Welcome to the final outcome on simple redox processes. We'll look at redox as the transfer of electrons, the idea of oxidation states, and how to write and balance redox reactions. In this outcome, you'll explain oxidation and reduction as electron transfer and link them to changes in oxidation state. You'll write and combine half equations, identify oxidizing and reducing agents, apply the rules for assigning oxidation states, and learn to read the Roman numerals that appear in systematic names and in oxyanions. The big idea here is that redox is all about electrons. The word redox itself combines reduction and oxidation, and the two always happen together, hand in hand. Electrons lost by one species are gained by another, and no electrons are ever created or destroyed along the way. This one process drives an enormous amount of chemistry, from batteries and corrosion to respiration and the extraction of metals. Let's define the two halves precisely. Oxidation is the loss of electrons by a species, and reduction is the gain of electrons. The memory aid to remember this is oil rig. Oil stands for oxidation, is loss of electrons, and rig stands for reduction, is gain of electrons. And both processes always occur together in every single redox reaction. A few terms to fix in place. Oxidation is the loss of electrons, and the oxidation state increases, becoming more positive. Reduction is the gain of electrons, and the oxidation state decreases, becoming more negative. A redox reaction is one where oxidation and reduction happen together. And an oxidation state is just a number showing how many electrons an atom appears to have lost or gained. Let's see electron transfer in a real reaction. Magnesium burning an oxygen to form magnesium oxide. Each magnesium atom loses 2 electrons, going to a magnesium 2+ ion. And that loss of electrons is oxidation, the oil part of oil rig. Meanwhile, each oxygen atom gains 2 electrons to become an oxide ion, and that gain is reduction, the rig part. The electrons lost by magnesium are exactly the ones gained by oxygen, so magnesium is oxidized, oxygen is reduced, and the magnesium oxide is ionic, made of magnesium 2 plus and oxide ions. We can show each part on its own, using half equations. A half equation shows only the oxidation or only the reduction, with the electrons written in explicitly. In an oxidation, half the electrons are lost, so they appear on the right-hand side, while in a reduction half, they're gained, so they appear on the left. And each half equation has to balance for both atoms and charge. Let's compare the two halves side by side. In an oxidation half equation, the species loses electrons, which are written on the right, as when zinc goes to a zinc 2+ ion plus 2 electrons, and its oxidation state rises from 0 to +2. In a reduction half equation, the species gains electrons, written on the left, as when a copper 2+ ion plus 2 electrons goes to copper, and its oxidation state falls from +2 to 0. Let's identify the two halves for zinc reacting with copper, 2+ ions, giving zinc 2+ ions and copper. Zinc goes from zinc to a zinc 2+ ion, losing 2 electrons, so the oxidation half is zinc goes to a zinc 2+ ion plus 2 electrons. Copper goes from a copper 2+ ion to copper, gaining 2 electrons, so the reduction half is a copper 2+ ion plus 2 electrons goes to copper. Check that the charge balances on each side, and you can see zinc is oxidized while copper is reduced. To combine two halves into a full equation, the golden rule is that the electrons lost must equal the electrons gained. So you multiply each half equation up until the electrons match, then add the two together. The electrons, now equal on both sides, cancel out, and you cancel anything else that appears identically on both sides. Finally, check that the atoms and the total charge balance in your finished equation. Let's combine two halves that don't have matching electrons. Aluminium going to an aluminium 3 plus ion plus 3 electrons, and a copper 2 plus ion plus 2 electrons going to copper. Aluminium loses 3 electrons and copper gains 2, and the lowest common multiple is 6. So we multiply the aluminium half by 2, giving 2 aluminiums to 2 aluminium 3 plus ions plus 6 electrons, and the copper half by 3, giving 3 copper 2 plus ions plus 6 electrons to 3 coppers. Add them, cancel the 6 electrons on each side, and we get 2 aluminiums plus 3 copper, 2 plus ions goes to 2 aluminium 3 plus ions plus 3 coppers, with a charge of plus 6 on both sides. Now let's talk about oxidizing and reducing agents. An oxidizing agent oxidizes another species and is itself reduced, which means it gains electrons. A reducing agent reduces another species and is itself oxidized, so it loses electrons. The trick to identifying an agent is to look at what happens to the other species. The agent does the opposite. Let's spot them side by side. An oxidizing agent causes oxidation in another species while itself being reduced, gaining electrons, so its own oxidation state decreases, like the copper 2 plus ion in the zinc and copper reaction. A reducing agent causes reduction in another species while itself being oxidized, losing electrons, so its oxidation state increases, like the zinc in that same reaction. Let's name the agents in the reaction of aluminium with copper 2 plus ions, giving aluminium 3 plus ions and copper. Aluminium goes from 0 to plus 3, losing electrons, so it's oxidized, and a species that's oxidized is the reducing agent. The copper 2 plus ion goes from plus 2 to 0, gaining electrons, so it's reduced, and a species that's reduced is the oxidizing agent. So aluminium is the reducing agent, and the copper 2 plus ion is the oxidizing agent. Let's check your understanding. Can you state what oil rig stands for in full? In the half equation, where iron goes to an iron 2 plus ion plus 2 electrons, is the iron oxidized or reduced? And if a species gains electrons in a reaction, is it the oxidizing agent or the reducing agent? Have a think. A few more terms. A half equation shows only the oxidation or only the reduction, including the electrons. An oxidizing agent is a species that oxidizes another and is itself reduced, gaining electrons. A reducing agent is one that reduces another and is itself oxidized, losing electrons. And an oxyanion is a negative ion containing oxygen bonded to another element, such as the chlorate ion. There's a second, more powerful way to define redox using oxidation states. An oxidation state is the charge an atom would have if all its bonds were treated as fully ionic, so it gives us a bookkeeping method for tracking electrons. In these terms, oxidation is an increase in oxidation state, and reduction is a decrease. The real advantage is that this lets us spot redox even in reactions where there are no free ions to point to. Here's the first set of rules for assigning oxidation states. An uncombined element is always 0. So that covers sodium metal, oxygen gas, chlorine gas, and so on. A simple monatomic ion just takes its charge, so a sodium ion is +1 and a sulfide ion is -2. Group 1 metals are always +1 in their compounds. Group 2 metals are always +2, and fluorine is always -1 in its compounds. Now the second set of rules. Hydrogen is usually +1, though it's -1 in metal hydrides like sodium hydride. Oxygen is usually -2, though it's -1 in peroxides such as hydrogen peroxide. The oxidation states in a neutral compound must add up to 0, and in an ion, they add up to the overall charge of that ion. So the method is to apply the fixed rules first, then solve for whatever's unknown. Let's find the oxidation state of sulfur in sulfuric acid. There are 2 hydrogens, each +1, giving +2 in total, and 4 oxygens, each -2, giving -8. Let the sulfur be X. Since the compound is neutral, +2 plus X plus -8 must equal 0. That gives X minus 6 equals 0. So X is +6. Sulfur is in the +6 oxidation state in sulfuric acid. Now the manganese in the permanganate ion. There are 4 oxygens at -2 each, giving -8, and we'll let the manganese be X. This time it's an ion with an overall charge of -1, so X plus -8 equals -1. That gives X equals -1 plus 8, which is +7. So manganese is in the +7 oxidation state in the permanganate ion. Let's try the chromium in the dichromate ion, which has 2 chromiums and 7 oxygens. The 7 oxygens at -2 each give -14. Let each chromium be X, and remember, there are 2 of them. The ion's charge is -2, so 2X plus -14 equals -2. That gives 2X equals +12, so X is +6. Each chromium is in the +6 oxidation state. Let's use oxidation states to prove redox in sodium reacting with chlorine to form sodium chloride. Sodium starts as an element, so its oxidation state is 0, and in sodium chloride it's +1, so it rises from 0 to +1, and an increase in oxidation state is oxidation. Chlorine starts as an element in chlorine gas, also 0, and in sodium chloride it's -1, so it falls from 0 to -1, and a decrease is reduction. So sodium is oxidized and chlorine is reduced. Let's look at Roman numerals in systematic names, because they carry real meaning. A Roman numeral gives the oxidation state of the named element. So iron 2 means iron in the +2 state, and iron 3 means the +3 state. That's why iron 2 chloride and iron 3 chloride are different compounds, and likewise copper 2 oxide is one compound, while copper 1 oxide is another. We use numerals whenever an element can exist in more than one common oxidation state. The same numerals appear in the names of oxyanions, which are negative ions containing oxygen, and another element. So chlorate 5 is the ion where chlorine is +5, and chlorate 1 is the ion where chlorine is +1. Sulfate 6 is the everyday sulfate ion, while sulfate 4 is the sulfite ion, and nitrate 5 is the nitrate ion, where nitrogen is +5. The numeral simply removes any ambiguity about the oxidation state. Let's confirm that chlorate 5 really does contain chlorine in the +5 state. There are 3 oxygens at -2 each, giving -6, and we'll let the chlorine be X. The ion has an overall charge of -1, so X plus -6 equals -1. That gives X equals -1 plus 6, which is +5. And that matches the 5 in the name chlorate 5, so the systematic name is telling us the oxidation state directly. Let's bring the 2 definitions of redox together. By electron transfer, oxidation is the loss of electrons, and reduction is the gain, which works best for reactions with clear ions and is shown using half equations. By oxidation state, oxidation is an increase in oxidation state, and reduction is a decrease, which works even when there are no free ions, and is shown by comparing the states before and after. 2 viewpoints, the same underlying chemistry. Let's finish with a check. Can you work out the oxidation state of nitrogen in the nitrate ion? What's the formula of iron 3 oxide, and what's iron's oxidation state in it? And in chlorate 1, what's the oxidation state of chlorine? Give those a go before you wrap up the unit.